going to look at multiplying vectors by scalars and seeing how our magnitude and direction are affected by the scalar. So let's just jump in. We're going to do a couple of examples, two of them actually. So the first example, we're going to look at the vector r. And r equals 9, 3. And the scalar that I'm going to multiply is 5. And to multiply a vector by a scalar, you multiply each of the components of the vector by the scalar. So in other words, I have 5 times r is going to be 9 times 5, 3 times 5. And then looking at this, 5r is going to be 45, 15. So now let's look at the magnitude. And what we're going to find is that the magnitude is going to increase by a factor of the scalar. So I'm going to do it two different ways. I'm going to do it 5 times my vector, or the magnitude of my vector. So this is going to be 5 times 9 squared plus 3 squared, which is going to be equal to 5 square root of 81 plus 9, which is 5 times the square root of 90. Placing that into my calculator, I roughly get 47.4. Now if I did this as 5 times my vector, I should do this in a slightly different color, so let me remove that. Went a little too far. I think I'm going to do this in orange. Times the vector r. We're looking at the square root of 45 squared plus 15 squared. And I'm going to put this directly into my calculator, and I actually get the same thing. 47.4. Alright, so it doesn't matter how I multiply this into my scalar, it works either way. But that's how it compares to the original vector, because the original vector is square root of 90, we multiply 9, or 5 to it. Where I got 9 from, I mean, I know where I got 9 from because I was saying 90. And then let's look at the direction. So theta, and I'm going to do theta just r. So basically the angle of my original vector. And the angle of my original vector is going to be the arctangent, or the inverse tangent, of 3 divided by 9. Which is not going to be something found easily on the unit circle, so using your calculator you get roughly 18.4 degrees. And then let's look at theta of 5r. Well, we're going to do tangent of y divided by x, which again is going to give us a rough estimate, and it's going to give us the same degree, because all we're doing is we're taking our vector and we're just extending it. We're not changing the angle, we're not doing anything crazy to it, we're just extending it. So the scalar product is 45 and 15 and has the same direction and 5 times the magnitude of r. Okay, so that's the first example. The second example, we're going to look at s. So the vector s is going to be equal to 4, 5, and we're going to multiply -3 to this. So now we're bringing in that negative factor. So the first thing I'm going to do is I'm going to do -3 times s is going to equal -12, because it's going to be -3 times 4, which is -12, and -3 times 5, which is going to be -15. Alright, so let's see how our magnitude is impacted by this. And remember, our magnitude is our distance from the origin to that point. So let's see, negative, I'm going to change my colors for this, for my magnitude. So -3, the magnitude of S is going to be equal to -3. The square root, that's a weird square root, of 4 squared plus 5 squared, -3 of 41. And this is going to be approximately, again, 19.2. If I did it the other way, if I did -3 of S vector, we get the square root of -12 squared plus -15 squared, which then now equals the square root of 369. Again, we get approximately 19.2. So my magnitude's the same whether I multiply -3 or 3. By the way, this is a magnitude, so I have to keep that absolute. So this is not -3, this is +3. Note that I left that out. I left that piece out. That's how we get positive here, because we're taking the magnitude, which is the absolute value. So key feature, make sure you have the brackets. You have the brackets. It looks like an 11. Those are the brackets. All right, so now we're going to look at, can you see this color? It's a hard color to see. So I'm just creating a new color here. Now let's see the direction. And to go back here, sorry, that's why I paused. I have a thought here. Because magnitude is a length, and length needs to be positive. That's why we take the absolute value, and that's why you need to have the absolute value in there. All right, so now let's look at the direction of this. And we're going to take the arctangent of 5/4. And here we get approximately 51.3. And if we take -3 times the vector S, arctangent of -15/12, which is going to be 15/12. This is going to be approximately 231.3 degrees. So the scalar product gives us -12 and -15. This has the opposite direction and is 3 times the magnitude of -S. So we're going the opposite way. Graphically, what this would look like is we originally were going this direction, and now with a -3 go this direction times 3. The magnitude of the resulting vector after the scalar multiplication is the product of the magnitude of the original vector, so nothing really changes there. And the absolute value of the scalar. And remember, I left the scalar out. I forgot to take the absolute value. Make sure you're taking the absolute value because we're talking about the magnitude, and the magnitude needs to be positive. The direction of the resulting vector is the same unless the sign of the scalar is negative. And then with that negative, re-rotate it 180 degrees. In other words, 180 degrees plus 51.3, because again, we are negative here, so we're rotating it 180 degrees, would give us the 231.3. All right, so there's 2 examples of multiplication of a vector. If you guys have any comments or questions, please feel free to ask, and I will catch you in the next video.